So, good afternoon again. We have a few new people here. So, welcome at this invited talk. And I'm happy to welcome top worldwide researcher in area of mobile networks, Professor Gesbert from Eurecom in France. He did his master studies in Paris. Then in Paris it was PhD, right? PhD
and master's also.
And master, okay. Then he spent a couple of years at Stanford in USA for postdoc, and he was also professor in Oslo in Norway, and now, well, after that he returned to France, to Eurecom, where he was professor and head of the department, and now he's director of Eurecom. And he will talk about 6G networks from the perspective of drones, where he did a great contribution together with his colleagues in Eurecom. So I'm looking forward to you.
Thank you, Zdenek. Very nice. Thank you. So happy to be here. So now I wear my hat as a researcher, not as a school director. So I realized when taking the plane today that this was my first trip to Czech Republic since 1991. So that really goes back a long time ago. 1991, I did a trip as a student with my girlfriend at the time. We took a train from Paris, not knowing anything, but the Iron Curtain had fallen maybe a year before that, barely. So it was the time just to discover Czech Republic. So we took the train and ended up on the train. And we did something. It has nothing to do with 6G, but this is interesting to show the evolution of times. We boarded the train with my girlfriend, and then in Paris, a guy came running after us and bringing us a big box and saying, "Can you please take this big box to Prague?" And we were a bit scared because we were going to cross borders, Germany, and then Germany to Czech Republic. And we did it. I took the box. Nobody would do this today, right? You would never take a box from a total stranger across different borders. So we did it, and which was crazy. And in the end, the box was completely fine. I mean, we opened the box in the train before the border just to make sure that we were not going to be caught by police. And there was a bunch of artist exhibition invitation cards. And when we ended up in Prague, we were greeted by this couple of artists from Prague who thanked us very much, and they invited us to their home, and we didn't have to stay in a hotel. And we will stay in a family like this for several days, thanks to this experience. So this is what I remember from Prague. Really nice experience. I do not recommend doing that anymore when you board an airplane, taking a box from total strangers. So this was 1991, long time back. So I'm very happy to be back. So I'm back because, as you understood from my previous lecture, Eurecom and C2 have been collaborating now for some time. C2 is a member of Eurecom, and we have collaborated with Zdenek together in the fields of using different things. But one of the things is using drones for future wireless networks. So this talk is about what can be done with drones in 6G, and how can you make those drones? How can you actually design actual robots that you can experiment with? And this is a topic that's a bit new for me at the time, because I come from communication theory and information theory, statistical signal processing. I never designed anything myself, except long time back I was working in a startup, but after that, in my research career, I only did theory and algorithms. But I wanted to try something a bit more hands-on, and this is also very useful to experiment and to work with students. Students really love to experiment with prototyping activities, and we've been very successful with that. So let me tell you a bit more about what we're doing here. I don't know if you recognize those pictures. These are, disaster areas. So It's hard to pinpoint exactly. Let me tell you where it was taken. So one it was taken recently in Valencia suburbs in Spain after the floods. Then last year there was a huge earthquake in Turkey. And then this year there was also a big disaster in the Florida area called Milton hurricane. So what's the common point between all these pictures? Well, you know, when you have a big disaster, flood may come in, water may come in, wind comes in and destroys everything. And even if there's no wind, water comes in and can destroy sources of power. So you may have power outages. And the impact of that is that it could bring down cellular service. So after a disaster of this kind, it's typical that you have hundreds of thousands of people with no connectivity, no internet, no phone, and sometimes lost. We don't know where they are, and there's no way to access those people. So the idea is, what if you could have tiny robots that could be launched by the service provider or by law enforcement? These robots could be equipped with radio equipment, similar to what is being used in 5G antenna towers in the city, except you would have to make it really much smaller, much more compact, equip that on a small flying robot, and have this flying robot be deployed as if the 5G network was now a flying network. You could do many things with that. You could try to restore connectivity services. You could use the robot as flying relays. You could use the robot as flying sensors that could listen to radio waves and try to understand where people are located. So you could perform localization tasks with that. You could use the drone as a relay between law enforcement on the ground and enable some kind of mesh network capability. You could do many things with that. And this was basically the premise of this research. So I'm not going to show you all those use cases, but I'm going to focus on 3 use cases today. One of them is just at the theory level, and the other 2 are all the way to prototyping, and I will show you some videos of what we have done. So the first one I will show you is about connectivity, and it's called energy efficient IoT data harvesting. So this is not, you could use that after a disaster, but in this case that we present here, it's another scenario, a little bit similar, but no disaster. Imagine you have an IoT setting where you have a lot of different sensors that have been deployed, for example, in a large factory setting or agricultural setting. And those sensors are collecting, they are measuring some data, and then you would like to help those sensors upload their data as efficiently as possible. Okay? So you could do that with a cellular network, and this is what is done today. But you could also use a robot that's going to fly around in some way and act as a receiver, act as a data sink for all these sensors that are uploading data to the robot. Okay? Why is it a good idea to do that? Well, because with a drone you can actually fly and fly closer to those sensors, and you can reduce very much the distance between the transmitter, which is located in the sensor, and the receiver, which is in the robot. And in wireless communication, when you reduce the distance between transmitter and receiver, you can use that to decrease a lot the transmission power that you need to communicate. So, and with that you can extend the battery life of your IoT network. The second use case is different. It's a use case about sensing and localization. Going back to my picture with disasters, imagine you have people who are lost, but they need to have a phone or a wireless device, and you want to use the robot to sense the radio waves and extract somehow patterns and use that to find out where those people are located. Okay? The third one is autonomous relay. So this is typically the case where, for example, so either you have a disaster, or maybe you don't need a disaster. Maybe you have a large crowd that is gathering for a sport event or concert, and you want to have additional connectivity capabilities, and you send a robot or multiple robots to act as a relay between the infrastructure and the people on the ground. So those are the three use cases. Let me start first with the one which is the more theoretically oriented. This is a use case that is quite challenging from an algorithm design point of view, because this is a scenario where almost nothing is known by the robot. So again, you have to imagine you have a large number of sensors that have been scattered around. I don't know where they are located, okay? I will make a few exceptions. I will assume that I have thrown a couple of sensors with non-location, but most of them I don't know where located. I ask a robot to take off and to fly essentially near the sensors, but I don't know where they're located. And I'm asking then the robot to collect the data from the sensors as quickly as possible. But the robot doesn't know the wireless propagation environment. It doesn't know the position of the sensors. And it doesn't know where it should be flying. So the notion of optimal trajectory is completely unknown by the robot upon takeoff. All of that has to be learned by the robot. So there's a lot of learning involved. Okay. And this is why it is challenging. So how do we address this problem here? All right, so let me just summarize my notation here. So I have an IoT network. I have K sensors, capital K. And I will be assuming that I have not just one robot, but M robots. Why do I do that? Well, if I have to cover a large area with many sensors, I'm hoping that with more robots, it will take less time for them to collect the data from the sensors. But to make sure that that happens, you need to enable some sort of cooperative behavior between the robots. So that's another thing to learn, by the way. The robots are not aware of each other's trajectory. So how do you make them cooperate and make sure that they deploy in areas that is optimally cooperative? That means not redundant. They should not follow each other, otherwise it's wasted resources. They should go in different areas. So this is a behavior you would like to also to enable. So M robots is the number of robots. What else? Okay, it's important. I will assume that I have an arbitrary environment with maybe it's I don't know, suburban, or something that is not flat. You have buildings, you have obstacles, so it's a little bit complicated. Sometimes you have line of sight between the sensors and the robot. Sometimes you have non-line of sight. Sometimes the radio signals are being obstructed. So I also assume that most of the sensors are at unknown locations. Okay, so this UK is something unknown. But I will assume also that I have a few sensors that I have placed myself at known places. Why do I do that? Well, because the robot will have to learn many things at the same time, and I need to find a way to initialize the learning process. So I need to give something to the robot initially. The way I will be able to localize the sensor, because this is something I will have to do implicitly, is by listening to the radio waves. And essentially, when you listen to the radio wave, measure the signal level, and you notice it's very low, you don't really know if it's because the transmitter is very far away, or maybe the transmitter is close by, but there's some kind of building in between, and the signal has been attenuated by the propagation. So there's this fundamental ambiguity that needs to be resolved. If initially you don't know the propagation parameters and you don't know the user location, there's nothing you can do. You cannot resolve the ambiguity. So the only way to resolve the ambiguity is to assume that you have a few nodes, we call them anchor nodes, at known locations. And that way you will be able to kickstart the learning process. I'll come back on that. So what is unknown otherwise? Well, the location of all the other nodes. The channel model parameter is also unknown. We take off, but we don't really know the propagation characteristics of this area. And the trajectory of the drones is, of course, completely unknown. This is what we need to determine, what we want to optimize. So there's a lot of stuff to learn at the same time. And of course, you can write down a complicated optimization problem, which looks like this. It says that I have a certain flying time. Let's say I want to fly 5 minutes, no more. That corresponds to a flying energy budget, B. And I say, within this flying energy budget B, and knowing that I know the starting place of the robot and the finishing place, okay, so this is the starting place, finishing place, I would like to maximize the total amount of data collected by all the robots. So I have M robots over N time slots. So this is the length of the trajectory, and collected over the K sensors. So I want to maximize this triple sum here. And how much is the data collected? Well, I use a classical wireless approach, where I say that the data I can collect is given to me by a Shannon type of expression, which is that depends, on the logarithm of 1 plus the signal-to-noise ratio. And the signal-to-noise ratio depends on the channel model. So, if you have a building between the drone and the sensor, the channel model would be in the first category. If it's line of sight, it will be a different category. But you don't know it in advance, because you don't know the location of the ground nodes. So you need to know that there are two kinds of channels. One are the line of sight channels, and the other one are the non-line of sight channels. So as you fly around, you need to measure the received signal level. You need to classify, try to guess, are you in line of sight or non-line of sight to every given sensor, and try to, at the same time, localize the sensor. Okay. You have to do that, and then later we'll talk about optimizing the trajectory, which is another challenging part. So, localization, learning, classification. So what we do is that we break this optimization problem into sub-problems, and this is where having anchor nodes become useful. So what we do is that for the few nodes for which we have the known location, what we'll do is that we will measure the received signal level at the robot coming from those particular anchor nodes. So for those, we know their location, so we'll be able to measure the distance. And I also forgot to mention, but I have a map of the environment. So I have a 3D map of the environments. I know exactly where every building is located, the height and the shape of every single building. Okay? Otherwise, you cannot do this. So by leveraging the 3D map, and for those sensors with known location, I observe the radio signal level, and based on that, I'll be able to derive the channel model. Channel model tells me how much signal power to expect at a given distance for long line of sight and for line of sight. Okay? Once I have the channel model, I can use that to try now to guess the location of the other sensors. How do I do that? It's non-convex optimization. I have to use another form of optimization approach. Here we use particle swarm optimization. So what does it mean? It means that you start off with wild guesses for the sensor locations, and then you try to eliminate bad guesses and only preserve the good guesses. What is a good guess? A good guess is something that allows you to match with the observation that you make about the signal power. So you keep all the candidate locations that seem to be fitting the received signal level that you're observing at the drone. Little by little, iteration after iteration, you converge to better and better guesses for the sensor location, and that's how you will be able to localize the sensors. Okay, so that's the rough idea of the algorithm for how to learn the channel and localize the sensors. At this stage, you noticed I have not optimized the trajectory of the drones. So there's no, it's arbitrary trajectory, and there's no cooperative behavior between the drones. So now I still need to enable that. So for that, we implemented an additional learning stage, which is taken from the framework of reinforcement learning. So reinforcement learning, in case you're not familiar, is an approach taken from the family of learning methods, which is suitable in cases where you have to learn an optimal strategy or an optimal set of actions based uniquely on observing rewards from trying different actions. So here, the reward is how much data you're able to collect from sensors. And what are the actions? Well, the action space is where is the drone going? So at different places, the drone will observe that is able to collect a lot of data from the sensors because probably it's closely located to the sensors. And other cases, it's not able to collect a lot of data. So by trial and error, you can, in principle, little by little, optimize the actions of the drones. That means optimize the places where the drone is flying. And that's how you can optimize the trajectory. The problem with reinforcement learning, if you have tried this approach, is that it takes a long time to converge. It takes a lot of trial and error. And this is not something you can afford to do when you have actual robots, because you have limited flying time, limited battery budget. So we need to find a way to accelerate the learning process. So there are two ways to accelerate the learning process. One is to use the notion of a model. In reinforcement learning, at first, you don't need any model. You'd only observe your rewards. And then you're going to give advantage to actions that seem to be giving you more rewards, and you disadvantage actions that give you less rewards. That doesn't require any model. But if you have some kind of wireless modeling expertise, why not use it? This is something you can implement into the reinforcement learning agent to accelerate convergence to the learning case. That's the first idea. Second idea is to have multiple robots and hope that they will be helping each other. Okay. So how do we do this in practice? So we use the reinforcement learning approach in each side of the drones. And in each side of the drones, we're going to embed a model. The model is essentially the one I presented below here. It's this one. Basically, it's a model that tries to understand how propagation behaves and also where the sensors are located. This is very powerful. It means now you have a reinforcement learning approach where each agent, when it's making a measurement of signal level, it's able to understand, to make sense out of it, and to explain it with physics. If you don't have a model, and if you observe that your received signal level is, 15 dBm, it's just a number. It doesn't make any sense. But if you say that, a signal level is actually the result of a model that looks like something like that, you're teaching something very useful to the learning agent. And you're helping to converge to a better actions much more quickly. Okay, so that's the basic idea. So this is an illustration of this behavior. This is a virtualized city here, and you see we took 3 drones. This is just a simulation for now. 3 drones, and this virtual city represents buildings by their heights, different colors. And then the stars and the triangles represent the nodes on the ground. Actually, the ones with triangles, they are the anchor nodes with known location, and the stars are the ones that are unknown. And now what I show here is the policy, the strategies, the trajectories followed by the robots after convergence of this algorithm. So as you can see now, each one of the 3 drones is following an independent path, nicely cooperative, because they don't step on each other's toes. They try to visit different subset of agents, and that way you're able to collect data as quickly as possible. Okay? So this was just an example. This is more of a, I would say, more meaningful performance evaluation curve, because this shows now for the similar situation, so three drones. And now what I'm measuring is that I'm measuring the data collection ratio. So if I get close to 1, so if I have enough flying time, normally I should be able to collect 100% of the data from the nodes. But if I have short flying time, I may not converge to 100%, but maybe I can converge to 90%, 80%. Okay, so if I get a curve that's as high as possible, it means it's better. And the x-axis is the time, is the number of learning episodes. So you want to learn as quickly as possible. So what do we compare here? So we compare the case of, so IQL is independent Q learning, is essentially reinforcement learning, but in a way that is not specialized to the case of multiple agents. So there's no cooperative behavior there. So what you see is that it's learning, it's collecting the data, but it takes some time before converging. QMix is an approach for reinforcement learning that allows multiple agents to cooperate with each other. So they are aware of each other's existence. But there's no modeling there. There's still no model about the physics. So you see how it has accelerated the learning process. The next step is to inject a model. And this is what we do with blue curve here, which is model 88 QMix. So in this case, much faster convergence. So you see the impact of exploiting your knowledge as a wireless expert is very, very important. The red curve, I forgot to mention, is an extra layer we call federation. Instead of letting each one of the robots converging with its own separate model, which could be inconsistent from robot to robot, we enforce consistency by asking each robot every so often to update, to send in the network their model, and then the network will compute an average of all the models and then send back the result to every single drone. So that way, you make sure that the drone have really consistent models about the reality. And that's another way to accelerate further the process. All right, so this was a first use case of what can be done with a robot to collect data from sensors that have been scattered around in an IoT network. Second use case, it's about localization and sensing. So let me say a few words about localization in 5G and 6G. So, but first of all, localization is one of the strong mandates of wireless networks from the time of 5G, to be able to localize radio nodes with a certain amount of accuracy as often as possible. Okay, it's never perfect. It can never be done all the time, but we try to make sure that it can be done most of the time with enough accuracy. So by enough accuracy, you know, we can talk about a few tens of meters. But this is not enough in some situations. You would like to have more and more accuracy. This is why in 6G, one of the KPI is going to be high accuracy localization. This is to localize people when they are lost, but this is also to localize robots, for example, in factories. In the factory of the future, you may have robots that are used, not the robots that I'm talking about here, the robots that are used to build cars in the factory. They'll be wireless, and you need to be able to localize the robots very accurately so that it's safe for people to interact with robots. And we're talking about, hopefully, centimeter-based accuracy. So localization is very important. How can you localize a radio node in a wireless network? Of course, you can use GPS, fine. But GPS has limitation. You know, if you have a non-line of sight environment, or if you are indoor, if you have strong obstructions from nature, the accuracy will not be good. So what can you do? Well, you can also localize from data coming from the network by using the notion of triangulation. Triangulation means that if you can measure the distance between one point which you want to localize, if you want to localize one point, if you can measure the distance between this point and at least 3 points of reference, then you can triangulate and pinpoint the location of that node. Okay. So how can you evaluate distance? Well, typically by using this time of arrival or time of arrival data from a path. So the time between the transmission time of the transmitter and the receiving time of the receiver. This is the time of arrival data. You can convert that into a distance, and if you have enough time of arrival data, you can triangulate. The problem is that if you have an area that's with buildings and obstacles, usually it's very hard to have high accuracy, because maybe you're measuring a time of arrival which is very long, so you have the impression that the node is very far away, but actually it's just that the path has been reflected on buildings, and therefore you get completely inaccurate measurements. So this is really a major issue in wireless network, how to properly localize radio nodes when you have non-line of sight environment. And what we said to this question here is that why not use robots? Why not you inject a robot which, in addition to the fixed base stations, will give you additional data which you can use to improve the accuracy of your localization algorithms? Why is it good to have a robot? Well, first of all, a robot can fly around and it will describe a trajectory and it will give you a large amount of additional data that is not available from the fixed base station. You will not get just 3 or 4 measurements, you will get thousands of extra measurements all along the trajectory of the robot. That's one. 2, you can actually instruct the robot to fly at location where line of sight probability will be higher. As you gain confidence about the location of what you're trying to find, you can get closer, and at some point you'll be in line of sight position from that object, and you will get very accurate localization information. Okay? So this is not something you can do with fixed base station. So with this idea, what we did is that we developed an algorithm, and here's what it does. So here, this is an illustration. This is just for one robot. The blue star are the location of the robot at different iterations. The yellow circle is the unknown node. Okay, so we want to localize that node. The green object is an example of a fixed base station. Okay? And this one, the purple, is just obstacle to show what happens when you have path reflection. So now we have different kinds of measurements. We have the time of arrival measurement at the robot along the trajectory, and then we also have time of arrival measurement at the base station. Okay? So what we do is that we set up a system of equation. The unknowns are the set of unknown locations of the users, and the observations are the time of arrival data along the trajectory of the robot plus the one at the fixed base station. We put all of that into a series of equations, and actually you can show that this can be solved using standard least squares approach. So you don't need to do a particle swarm like before. This is actually standard optimization. And you can find the location of the user which makes those observations the most likely, maximum likelihood estimation. So this is actually summarized in a paper. I've given you the reference here. What is the next step? Now, if you noticed, this robot is flying at arbitrary location. But I could also formulate an interesting question, which is, what if I was trying to find the trajectory of the robot, which within a limited flying time, let's say 1 minute, will give you the best possible estimate of the unknown user location? That seems challenging, but actually it's doable. In robotics, this kind of approach is called active learning. In active learning, you have a bunch of data, and you try to learn from this bunch of data. But there's too much data, and you want to discard the bad data and only keep the data that is the most meaningful for your problem. Okay? Active learning. This is exactly what we do here. By instructing the robot to fly at certain position, I'm actually producing measurements that are maximally meaningful about the problem I'm trying to solve. I will go to places where this reveals the most information from an information theoretic perspective about the user location, and I will not go and fly at other locations that do not reveal much information about it. Okay? So that's the rough idea. So how do we do this? You need to have a metric. So this metric should reflect this notion of information about the user location. There are different ways of doing this. What we do here is that we use a metric called the Fisher information matrix. The Fisher information is a statistical metric that tells you how much information can be extracted from an unknown parameter just based on observing the realization of a random variable that depends on that parameter. And just looking at the distribution of that random observations, it will tell you this is the best you can do. No matter what algorithm you will ever use, no matter what estimation algorithm you will ever use, the bound will be dictated by the Fisher information matrix. Okay? So we use that. We use this KPI, this Fisher information, and we simply try to describe a trajectory which, step by step, is increasing the Fisher information KPI or metric. Okay? So we use a greedy approach. Okay, details are in the paper. This is an illustration, not yet prototype. I will show you the prototype after. This is the trajectory that is optimally designed from this information KPI point of view in order to, well, it was too fast, but basically we try to localize the unknown sensors here, the unknown nodes, and those were the fixed base station. Maybe I should try, let me, one more time. So you can see how the estimated location got closer and closer to the true location as the drone was flying around. Okay, you see the yellow stars coming up to the dark stars. It means that you're able to estimate the location of the sensors. In fact, you don't even need to wait for the end of the trajectory. You could do it much more quickly. So it depends, of course, on the situation. So this is actually a more meaningful curve, which is more like Monte Carlo curve. So we do averaging over many cases. So what we looked at is the localization error and the distribution of it. This is the CDF curve. Okay? So the CDF curve means that you want your curve to be as much as possible to the left side. Okay? So a CDF curve means that here, 50% of the time, you have a localization error in the blue case of less than maybe 1.5 meter. Okay? In the black case, you have a localization error of less than 12 or 15 meters. 50% of the cases. So what are those cases? Well, first, try to localize. So this is, by the way, a non-line of sight environment. So lots of buildings. This is a 80 megahertz resolution system. That means that in the very best case, your time of arrival is going to tell you something about the distance, but up to a certain amount of noise, which is dictated by the resolution. So if you have infinite resolution, you could have exact resolution, exact estimation of the distance. But if you have 80 megahertz, basically you have 3-4 meters of accuracy. That's the best you can do, regardless of algorithm. Okay, so you cannot hope to get more than that, at least in terms of guarantee. You could get lucky, of course, but in terms of guarantee, you cannot hope more than that. Okay, so this is what happens if you try to localize with just base stations, so fixed base stations, 5 base stations. Okay, so you get 50% of the time you can localize with 50-meter accuracy. Now you replace one base station by a robot like this. Okay, so 4 base stations plus a flying robot. And now you see the quite improved situation. But this case, the trajectory is not optimized yet, no active learning. And in the blue case is when you use active learning, you actually optimize the trajectory to have the best possible job at localizing the ground node, and you get another gain here. All right? Okay, so I wanted to show you also some videos, and I told you in the beginning that one of the challenges of this work has been that we wanted to derive and to design actual prototypes. So this is a picture of the kind of drones that we design in the lab. So the size of which is about this, I would say, like maybe 80 centimeter diameter or span of the wings. What the box you see below here is actually a full-fledged 5G base station. So it's something that would normally take a huge amount of space on a network provider antenna. Here is miniaturized, more compact. We also had to design new, I mean, this is quite challenging. There's a lot of interference. The power amplification was also an issue. We had to design our own power amplifier to fit in that box. You also had to design properly the antenna system, because there's a lot of antennas. You have antennas for the GPS. You have antenna for the remote control of the drone, because you still need a pilot for safety reasons, even though the robot is autonomous. In practice, you need a pilot when you do tests for safety reasons to gain control in case something goes wrong. So you have antennas for that, and then you have the 5G antenna. You have 2 kinds of antennas. The robot actually is acting as a 5G client, so it has the equivalent of a phone in there, and it has also the equivalent of a base station. So lots of antennas. You need to optimize the deployment of the antennas. So if you're interested, I can discuss later more the challenges, the practical challenges of designing such a robot. For the protocol stack, I mentioned earlier OpenAir interface as one of the software developed by Eurocom. We actually leveraged that in that prototype because we don't have Nokia or Ericsson equipment on campus. We have just off-the-shelf antenna, radio cards, and everything else is open source. That's the way you can actually dig in and access all this time of arrival parameter and play around with it, design algorithms. So open source is absolutely critical here. So we use OpenAir interface for that. And that's it. Let me show you now how the results, if I manage. So what you will see now is an experiment that we did in August on the campus. So we put, let me show you. We put a terminal somewhere in the forest around the campus. We also have our own base station, 5G base station on the rooftop. And then we have this drone. And what you will see is that the drone is going to move around to try to, well, listen and localize the user client. To make it, well, let's see. Yeah, this is what you will see. So this is actually what you will visualize is what's being done inside the robot. So this whole software that has been developed also by my colleagues using this Q ground control. This is a setup for robotics where you can visualize the in 3D the actions of the robot, and this is useful to understand the behavior of the algorithm. I will try to explain. No, this is not what I wanted to do. We go back to this one. Okay. All right. Wait, I don't need remove the sound here. I hate this sound. Okay. Okay, apologies. So this is the video we published recently on YouTube. You can actually find it if you're interested. Okay, so we have this guy here is going to be placed on the campus around here, okay? The drone doesn't have to actually go physically to the UE to localize it. It only does that from remote by listening to the radio waves. So don't expect the drone to actually go and physically jump at the user. It's not happening like that. Okay, so the drone, and what you see is the drone, but the hidden UE is actually in the forest. It's difficult to capture in the same video both, so you only see the drone. But what you see here is what's going on in the algorithm. This is the true user location, and this is step by step the estimation done by the drone. And the red dot tells you what is the next step that the drone decides to make. So sometimes the drone is a bit confused and may come up with a bad guess, and then it fixes the next iteration. Okay. So in this experiment, this is I think about the best it does. So this is about, I would say, 5-meter accuracy, but we have our bandwidth of only 40 megahertz. So this is about the best you can make. To have more accuracy, you will need a more bandwidth. All right. Last case, and last case, I will go very fast because I will not show any algorithm, nothing. Just to show you an example of realization. We also derived algorithms this time to do optimal relaying. So in this case, what you will see is that you will see the drone acting as a relay between our fixed infrastructure and a terminal. To make it more fun, the terminal will be also on a drone. So maybe it's a drone that is used to, I don't know, to deliver goods on eBay or something. It's not there to do radio services. It's only there to do its own life, but the problem is that it is not being covered by our 5G base station. So we need a drone to act as a relay between the client and the network. Okay? So let me show you. So I forgot if this one is the client or the relay. We will see, depending on which one is the next. Okay, so this one is the relay, and this one is the client. So what you will see is that the client is going to move around. So there's we move on purpose, we move the client on purpose. And then when the client is moving, you will see the relay adjusting its position automatically to serve as optimal relay at all times. How does it do that? Well, you want to optimize the throughput between the network and the client through the relay. So you need at all times to maximize the minimum between the throughput of the network to relay link and the throughput of the relay to client link. And this is why you see the relay moving around to kind of adjust its position. All right, I stop here. I've been speaking for a long time already. If you want more details, there's a web page where our list of papers and more details about the experiments are being revealed. And also on YouTube, we have additional videos that we publish on this. Thank you so much. If you have questions, I'll be happy to answer. Thank you.
Thank you very much, David, for a very interesting talk. Now, time for questions. Okay.
Okay, so I was just wondering regarding the second use case, the localization. Did you try to localize moving objects? Because if it's working, or the accuracy? Because I imagine that it's possible to do it if the users are static or any nodes, or that you want to localize. But what about moving objects? Did you try?
So as long as the object you're talking about is a radio device which is attempting to connect to a wireless network, we can localize it. Of course, if it's moving too fast, we cannot track. But this is in the end, this is an iterative algorithm. So by nature of the algorithm, if the user is moving around slowly enough, we can track, no problem. So it's a matter of speed.
And the convergence, like to localize it to...
You will lose. You will lose as the speed of the user is increasing. I guess you will see some worse and worse performance there.
So did you try to?
No, I didn't try yet.
Okay, thank you.
But it's a next step to do. Yeah, you're right.
Okay, I was expecting a question regarding relaying because it's your field, but okay. Other questions?
Thank you for your talk. The channel models, do they all rely on some globally available information or on some information about the environment, about the global environment, or can they be limited to only a local knowledge, or for example, some myopic channel estimation or something like this?
I'll tell you, the channel model, in fact, I mentioned something about physics and equations. We don't even use that. It's a neural network, and we optimize the parameters of that neural network to fit the observations.
Yes, but to this end, the robot needs to know about the environment, like where those buildings are and how high. Yeah.
The robot needs to have the knowledge of the 3D map of the environment.
It has to. So did you try like some methods which do not rely on this global information?
No, I mean, I guess you could learn. Actually, you know what? It's interesting, but in the beginning of the research project, we also designed algorithms to derive radio maps from radio measurements. And based on radio maps, you can also derive the 3D maps. It's possible. But in that case, you need to know the location of the transmitter and the receiver. So if you give me the location of the transmitter and receiver, and if you tell me how much signal level you observe, then if I get enough observations, I will be able to reconstruct the 3D map by myself. But now, if you tell me I observe a signal level and I don't know the map, and I don't know where the transmitter and receiver are located, no, it's too much. I cannot do it.
May I have another? Yeah. And if I may have another question, when you did the localization path planning, was it a one-off planning or did the robot replan? Maybe I missed it in your talk.
It's like this. It's an iterative algorithm. So it's a greedy algorithm.
So at the beginning of the drone flight, the path is fixed, or does it evolve during the flight?
No, it evolves during the flight. Yeah.
Okay, thank you. Thank you very much.
Okay.
Is it possible to use also airplanes instead of quadcopters that can hover in air, because quadcopters do not have a long battery life? So airplane drone.
Yeah, it's you mean fixed wing.
Yeah, fixed wing aircraft.
Wing. You will save on battery, but the problem is that in terms of agility, is not comparable to what we try to do here. So I would say it depends on the topology. So if you have a setup where your ground nodes are highly scattered, far away from each other, then there's enough amplitude of space for you to move around between the sensors with a fixed wing. That's fine. But if you have a high density of nodes, there's no way you can do with fixed wing, because fixed wing has minimum speed. It has a lot of requirement to turn around, and you won't be as precise as what we can do with the quadcopter.
So there is no need to stop in mid-air to measure for a longer time, like the quadcopter was stopping in the video?
In the prototype that you show, yes, we discretize the trajectory, but you can choose the discretization step, and every time you make measurement, yeah. There's a question in the back there.
Thank you so much for can you hear me? Thank you so much for the talk. Welcome. I have a question. Like, you use the energy consumption with the function of time, like 20, if I am not wrong in the slides. So the energy consumption with respect to the time, 20-minute flying time of the, what can I say, the robot. But the thing is, there is a learning algorithms and finding the path running on the drone. So is the energy consumption exceeds like more energy consumption with more running of the functions to find out the path of find out the trajectory to the destination. So isn't it change with respect to valuation?
Let me see if I understand the question. Let me go back to this one here. So if you have an algorithm that needs time to learn, then you need to take that into account into your energy expenditure, right? You can define the problem in the way you like, but typically what we do is that we use the learning algorithm to converge to an optimal trajectory, and it is that trajectory that is allowed to spend the given amount of energy. So I don't include, if you want, I separate the energy spent into the learning phase. There's a lot of energy spent in learning phase here. Okay, I try to minimize it, but I don't have a constraint for it. Yeah?
Thank you so much.
Maybe I would like to ask about the relying. You said that the relying was trying only using 5G, or you have tried some different, like Wi-Fi or another technology?
No, you could use. First of all, it's not easy to get good outdoor coverage with Wi-Fi, so this is difficult, and our drones are mainly outdoor drones. But in principle, you could use the same principle indoors as well if you wanted to. But the other advantage of 5G is that you can have this open source software that we can use to access the measurements, the parameters that we need for the algorithm. I don't know how to do that with Wi-Fi. I don't have an open source version of Wi-Fi that I can play with.
Okay, and if we are using the 5G, the drone which is used for relying, it's using like the GNB or the UE, or there are like two computers on the drone and they are like locally forwarding the data, and it's like the two separate sites?
Yeah, it's a good question. So it's like this. This guy in the middle is the relay. So in fact, the robot, and this is what I showed you in the picture, this robot has both a terminal, so a UE client, like a terminal, that it's using to communicate with the 5G base station. And it also has a G0B, which the final client is used to connect to the relay. So that's how we do it.
Yeah, thank you very much.
And we transfer the data from the UE to the G0B inside the robot.
Who else?
Okay.
Nobody. I have one short question. In your algorithm for multiple UAVs, is the first part of the presentation. Yeah. Do you consider interference, or how the UAVs share?
No. Yeah, there's a resource allocation protocol. So basically there, if you notice, there's no interference. That means that there's actually, I forgot to say, but there's a scheduling algorithm also that decides, typically you get the data from the transmitter that you're the closest to from a channel point of view. Mm-hmm. So the scheduler only collects the data from the strongest sensor around. And that's the one that gets priority. And then as you move around, you connect to another sensor because it becomes the sensor that is now the closest. You understand what I mean?
Yeah,
no interference.
I was just wondering whether it could be substituted with maybe shared resource communication so that everybody would use the same resources. But there will be interference, so there are pros and cons, and maybe it would be another dimension of the problem. Okay, thank you. No more questions?
It was already good questions.
Okay, thank you again.
Thank you.
For your
talk.
Thank
you so much.
And that's it. So thanks again for coming, and
if you're interested in the slides, maybe I can send you.
Yeah, maybe those who would be interested in slides, we will make it publicly available. The talk is recorded, and if David will agree, we will also publish it so that you can go through it again in the future. Thank you.